In the winter of 1709, Paris fell to -23 degrees Celsius. The Seine froze nearly half a meter deep. Saltwater harbors on France's Atlantic coast froze. Wine turned solid in cellar bottles. Trees split as water froze within their trunks. Livestock died in stalls, and the olive groves of Provence were killed to their roots. The harvest failed. Bread prices tripled. An estimated 600,000 people died in France from cold, famine, and the diseases that followed. This was the accumulated legacy of the Maunder Minimum, the 4 decades of suppressed solar activity between 1645 and 1715. It was not one terrible winter. Repeated failures spread across Northern Europe, Scotland, Scandinavia, and the German states. At the time, the North Magnetic Pole sat approximately 2,200 kilometers southwest of its present position, in the Canadian Arctic. In the manuscript's model, its primary radius covered Greenland, Iceland, and the North Atlantic. Its outer primary zone covered the British Isles, Scandinavia, and Northern Europe. The radius zones produced 1709. Those zones have since moved 2,200 kilometers. The framework does not expect the next minimum to reproduce 1709 in the same geography. It expects an equivalent atmospheric stress to fall on regions with no cultural memory of primary zone conditions. Episode 4 maps that rotation, where the zones were, where the manuscript places them now, and how its predictions can be tested. The radius model defines each zone through historical consequences, not arbitrary lines. The inner primary zone is where agricultural civilizations ceased to exist during severe minimum conditions. Greenland's Norse settlements had endured for nearly 4 centuries. They maintained farms, churches, contact with Iceland and Norway, and a functioning European society. The final confirmed record is a marriage in 1408. When Europeans returned later, they found ruins. The Thule Inuit survived and expanded. Their Arctic technologies, hunting systems, and traditional knowledge gave them resilience that European agriculture lacked. Within the framework, the lesson is not that the people lacked character. Their social system was not adapted to the zone. The manuscript places the coming inner primary zone over the Taimyr Peninsula, the Laptev Sea coast, and the northernmost reaches of Siberia. These places are sparsely populated and not agricultural civilizations like Norse Greenland. But the historical warning remains: the inner zone is lethal to human systems that cannot adapt. This is the steepest part of the radius gradient. It does not mean one sudden catastrophe. It means progressive attrition as growing seasons, energy demand, infrastructure, and the economics of habitation move beyond the limits for which a society was built. The outer primary zone is where civilizations survived, but famine reshaped them. Scotland's 7 ill years of the 1690s brought repeated harvest failure. Grain did not ripen in cold summers. Early frost killed crops before harvest. Wet conditions caused them to rot. In some regions, 5 to 15% of the population died. Migration to the American colonies accelerated, changing the Atlantic world's cultural geography. In the manuscript's next minimum map, this zone includes northeastern China's grain provinces, the Russian Volga and Krasnodar grain belts, northern Kazakhstan, and Mongolia. These populations are vastly larger and more integrated into global food markets than 17th-century Scotland. The secondary zone is different. It produces serious disruption, elevated mortality, difficult harvests, and political stress, but institutions remain continuous. France in 1709 was devastated, yet it remained France. Its agricultural system recovered. The model places Northern Europe, Scandinavia, Iceland, and the British Isles in the next secondary or extended zone rather than their historical primary positions. Their risk does not disappear, but the manuscript describes this as a structural improvement. 3 bands, 1 gradient, inner primary attrition, outer primary famine, secondary disruption with institutional survival. The model now rotates those consequences from the old pole position toward the Russian Arctic sector. The manuscript calculates the rotation from the pole's displacement. It places the Maunder minimum pole near 80 degrees north, 95 degrees west, in the Canadian high Arctic. It places the current pole near 86 degrees north, 139 degrees east, in the Russian Arctic. Across Earth's surface, that movement is approximately 2,200 kilometers and roughly 95 degrees of longitude around the polar region. Because the zones are organized around the magnetic pole, they rotate with it, though their boundaries are not simple straight lines. Latitude and the elliptical geometry around a near-polar point change the exact result for each region. In practice, the manuscript moves Iceland from inner primary exposure toward secondary or extended exposure. Northern Scandinavia moves back from outer primary conditions. Northern China and Mongolia move forward into the outer primary zone. Northern Russia and Siberia move into inner or outer primary exposure depending on location. The qualitative picture is the central claim: the regions that carried minimum period stress during the 4th century instrumental record are stepping back, while a Russian Arctic-centered sector steps in. That claim creates a geographic test. If the severe effects remain concentrated in historical northern Europe and northeastern North America while northeastern China and Mongolia remain comparatively stable, the radius model fails. The rotation is meaningful only if consequences rotate with it. The framework calls its predictions science rather than prophecy because it states what would prove them wrong. Its primary prediction is that the next significant solar minimum will concentrate the strongest agricultural disruption, cold anomalies, and social stress in the rotated radius zones rather than the historical ones. Confirmation would include several consecutive years of below-average grain yields in northeastern China while northern Europe performs normally or better, East Asian polar vortex penetrations increasing while North American disruptions decline from their historical frequency, and Mongolian livestock mortality from ZUD events exceeding the 20th century baseline. Falsification would look like a 1709 equivalent Paris winter while Harbin remains within normal variation, repeated Scottish harvest failure while Heilongjiang grain remains stable, or historical zone geological activity returning while the new zones remain quiet despite the conditions the model identifies. The manuscript expects evidence to accumulate as the solar cycle descends through its projected minimum, with enough data by approximately 2035 for a meaningful interim judgment. The framework is offered to be tested, not believed. Its predictions are on the table. The geographic distribution of future effects will decide whether the radius is a working model or a failed hypothesis. Chapter 12 begins in the spring of 2030 with a hypothetical farmer, Wang Jianming, planting wheat in Heilongjiang province on the same black earth farmed by generations before him. He does not see a magnetic map or a solar cycle. He sees a late frost, soil running 2 weeks behind the old schedule, an autumn frost arriving early, and grain yields that no longer match the almanac his family trusted. The manuscript places this experience inside a solar timeline. Solar cycle 25 peaked in late 2024 and early 2025, stronger than cycle 24. It states that this complicated earlier grand minimum forecasts and required the expected timeline and depth to be recalibrated. It projects cycle 26 beginning around 2030 at below average strength, and cycle 27 around 2041 potentially weaker again. It also states plainly that current data cannot determine whether these cycles will constitute a true multi-decade grand minimum comparable to the Maunder period. The model does not require Maunder-level severity to be tested. It argues that a moderate extended minimum should still express effects in the new radius zones. Severity controls magnitude. Pole position controls geography. For Wang Jianming, that distinction becomes a calendar: how many frost-free days remain between planting and harvest. Heilongjiang, Jilin, and Liaoning hold approximately 100 million people and form one of China's critical grain regions. Their rice, corn, soybeans, and wheat depend on a growing season of roughly 150 days. The margin is thin. A last frost 2 weeks late postpones planting. A first frost 2 weeks early ends harvest before grain matures. Both in 1 year can cause severe loss. Repeated together across several years, they challenge the entire agricultural system. The book emphasizes the adaptation gap. The region's varieties, planting dates, storage systems, and financial assumptions were built for the climate of the last century. Knowledge of 130-day crops, handling wet early harvests, and surviving repeated failures is not deeply embedded because primary zone conditions are outside living tradition. Humans will adapt, the manuscript says. But variety development, distribution, changed practice, and institutional learning take time. The dangerous period is the transition after the old climate regime stops matching expectations and before the new toolkit has reached the farm. The framework predicts northeastern China would enter that transition during the minimum's peak years. The risk is not a lack of ingenuity. It is the speed at which a system serving 100 million people must change. On the Mongolian steppe, approximately 1 million people depend on nomadic or semi-nomadic pastoralism. In good years, rainfall supports large herds. In Adzud, deep snow, ice, or extreme winter conditions prevent livestock from reaching food. The Adzud of 2009 and 2010 killed approximately 9 million animals, about 1/4 of Mongolia's livestock. Tens of thousands of families lost food and income, and international assistance was required. The manuscript treats that event as secondary zone variability, then predicts that outer primary conditions could produce severe events more frequently, perhaps several in a decade rather than once in a generation. Farther north, Siberia presents a different vulnerability. Cities, railways, roads, pipelines, and buildings were engineered for extreme but historically predictable cold. The framework does not simply predict colder averages. It emphasizes volatility, rapid changes and repeated freeze-thaw cycles. For infrastructure built on permafrost, thaw and refreezing can destabilize foundations. Ground subsides. Roads crack. Buildings tilt. Pipelines shift. These stresses compound damage already projected under warming scenarios. The Mongolian herder and Siberian infrastructure worker face different systems, but the same transition problem: institutions designed around 20th century variability encountering conditions the model places outside the design history. What does a primary zone feel like? The manuscript returns to historical testimony. Iceland lost approximately 1/4 of its population during the late 17th century through accumulated crop failure, livestock death, and disease. Reserves could cover one bad year, but not 3 consecutive failures. Greenland's Norse settlements ended. Scotland's 7 ill years left grain unripe beneath early snow, families without food, and a rural social order close to breaking. The book does not claim the next minimum will equal Maunder severity. It uses these cases as the qualitative boundary of primary zone risk, not inconvenience, but the point where climate becomes incompatible with systems that were never designed for it. The Southern Hemisphere has a parallel. The manuscript describes Southern Australia's cool season rainfall decline and Northern Australia's strengthening monsoon as an already measurable bilateral split. It predicts those trends will deepen during the minimum. For Western Australian wheat growers, less winter rainfall threatens the present grain belt. In the Northern Territory, greater monsoon rainfall increases flood and infrastructure pressure while potentially improving dry season livestock carrying capacity. New Zealand remains buffered by ocean but faces greater southern variability. The radius is a gradient in both hemispheres. Its consequences depend on what each society has built, planted, and learned under the climate it assumed would continue. The preparation window turns geography into action. For northeastern China, the manuscript calls for cold-resistant, short-season crop varieties, storage capable of handling early wet harvests, and agricultural guidance for altered planting and harvest dates. For Mongolia, it calls for emergency feed reserves positioned before winter, veterinary capacity prepared for stressed herds, alternative income for pastoral households, and a proactive rather than reactive international response. For Siberia, it calls for wider permafrost monitoring, conservative construction standards, and contingency planning for pipelines and power systems before extreme events. For southern Australia, it identifies water capture and storage, faster adoption of drought-adapted varieties, and investment in northern production capable of replacing some southern losses. These are not exotic technologies. They are the familiar work of agricultural adaptation, winterization, engineering margins, and reserves. But timing determines their value. Preparation before disruption is prevention. Preparation after disruption is emergency response. The framework says planetary physics provides the warning, but cannot make the human decision. Whether the next minimum becomes managed disruption or unmanaged catastrophe depends on what institutions do while the window remains open. Chapter 13 begins with the ordinary appearance of disaster. When the Akkadian system entered decline, a low river and a short barley crop may have looked like familiar drought. What its administrators could not see was that rainfall was changing across the entire radius geography, from the Mediterranean toward the Industry. Every affected civilization needed grain in the same years. There was no outside surplus waiting nearby. Modern disaster planning assumes geographic containment. If one region fails, another exports food, credit, fuel, and assistance. The global food system depends on disruptions being partly independent. The radius model violates that assumption. Regions within the same zone do not experience identical weather, but they face directionally correlated pressure at the same time, shorter growing seasons, disrupted rainfall, and lower yields across multiple producers. This is why the manuscript's disaster map matters. It is not a calendar of exact events. It is a structural risk map showing where simultaneous stress could defeat diversification strategies built on the old geography. The book assigns 4 agricultural tiers: abandonment risk in the inner primary zone, sustained famine risk in the outer primary zone, institutional resilience tests in the secondary zone, and biological cascade risk across the extended zone. Tier 1 covers the northernmost Russian agricultural margins within approximately 1,500 kilometers of the pole. The risk is progressive abandonment as growing seasons and operating costs make sustained settlement uneconomic. Tier 2 extends roughly 1,500 to 4,000 kilometers and contains the most consequential food risks. Northeast China produces a major share of China's grain. The Volga and Krasnodar belts support Russia's position as a leading wheat exporter. Stress there transmits through markets to countries dependent on Russian supply. Kazakhstan, Mongolia, and Kyrgyzstan form a steppe corridor whose pastoral economies are sensitive to drought and cold and whose safety nets may struggle with multi-year pressure. Tier 3, approximately 4,000 to 6,000 kilometers from the pole, includes Northern Europe and the East Asian coastal economies. Northern Europe retains adaptations built through centuries of harsher exposure. Japan, Korea, and coastal northeastern China face infrastructure stress from unusually frequent cold incursions. Tier 4 extends into the Horn of Africa, Arabian Peninsula, South Asia, and Sahel. Here the framework predicts biological cascades rather than direct cold, alternating drought and rainfall creating locust breeding opportunities, disease vectors, and crop pathogens in already stressed food systems. Different tiers. Different failure modes. 1. Correlated geography. Infrastructure fails when conditions exceed its design envelope. That envelope comes from the historical record plus a safety margin. The radius rotation creates a mismatch. Energy, water, transportation, and buildings in the new zones were designed during secondary or extended zone climate history. The book uses the 2021 Texas freeze as a small-scale illustration. Infrastructure built for subtropical conditions failed when extreme cold arrived. In the new zones, the exposure spans cities of millions and continental resource networks. Heating demand can exceed generating capacity while gas equipment freezes. Wind turbines ice. Solar panels collect snow. Hydroelectric systems face ice and altered flow, while backup generation experiences the same stress. Water systems face burst pipes during cold events and longer-term disruption when snowmelt, monsoon, and groundwater recharge stop matching their design assumptions. The response is technically understood: winterize gas infrastructure, increase reserve margins, build cold-rated backup capacity, distribute energy storage, protect pipes, and design water systems for greater variability. The difficulty is scale and time. Infrastructure can be strengthened gradually before a crisis or rebuilt rapidly after failure. The physical work may be similar. The human and economic cost is not. Climate stress does not automatically cause political collapse. The manuscript states that outcomes depend on institutions, leadership, support, and the exact form of pressure. It does not assign exact collapse dates. It identifies structural vulnerability. Mongolia receives the highest acute risk designation because so much of its economy and identity depend on pastoralism, while its fiscal capacity may not absorb repeated ZUD-scale emergencies. The Central Asian steppe is identified as a migration origin corridor. Historically, reduced carrying capacity moved populations toward surrounding civilizations. Modern states are not ancient nomadic confederacies, but food and income loss can still drive people north into Russia, east into China, and west toward Europe while those receiving systems manage their own stress. The key preparation gap is timing. Cold-tolerant crops may require 5 to 7 years from research to widespread adoption. Grain reserves are cheaper to build during ordinary harvests than during panic. Winterizing equipment costs less than replacing destroyed networks. Every year before disruption improves the ratio of prevention cost to response cost. Every delayed year narrows the options. The radius has rotated. The manuscript says risk models calibrated to the old pole position carry uncharted exposure. Institutions that read the new map can choose managed disruption. Those that do not may discover the map through failure. Episode 5 translates the framework into strategy and markets.